Welcome back to our statistics class notes, everybody. Just to remind you, we were walking through what the central limit theorem for the sampling distribution of p hat tells us, or the central limit theorem for population proportions is typically what it is, but it tells us about the sampling distribution of p hat. And on the previous page, on page 101, I was showing you how the reason we didn't get a nice unimodal symmetric distribution when we had our second simulation where I had 10,000 samples of size 10 was because the sample size was too small. So I just got done talking on the previous page again about what are the three conditions for the central limit theorem for sample proportions. And the problem is that you have to have a large sample. You have to have at least 10 successes and at least 10 failures, or 10 yeses and 10 nos, however you want to think of them. Okay, so when we got to looking at samples of size 100, right, I still had a population of size 1,000. I had 250 walkers in it, so a yes would have been getting a walker, a no would have been getting a runner, okay? Then I took 10,000 samples of size 100 and I plotted all my p hats, and I got a nice, beautiful, symmetric unimodal distribution, with the mean being the true population proportion p of 0.25 or 25%, and the standard error being this guy right down here, p times 1 minus p divided by n, which is, take the square root of that, which is the square root of 0.25 times 1 minus 0.25 divided by 100. Sample size was 100, which came out to be 0.0433. Now, why did this satisfy the central limit theorem? Because I had random sampling. There was a large sample size, n was 100, and n times p hat, or if I want to use n times p because I knew p, I should have expected about 25 in my sample to be walkers, which is certainly more than 10. And then n times 1 minus p, since I knew it, I should have expected about 75 in my sample to be runners, which certainly is more than 10, so I had a big enough sample size. And also the population size, which is 1,000, is 10 times larger than the sample size. So that's right on the border, but it was 10 times larger than sample size, which gave us a good unimodal symmetric, basically normal distribution. Okay, and the next example I'm going to walk you through here is example 133. Okay, I'm going to actually come back to this in my next video because it goes on to the next page and I want to get it all in one video.